Welcome back to Carneades.org. Today we're going to be continuing with our series, Dumbfounding Definitions, Dizzying Distinctions, and Diabolical Doctrines, a series sorting through some of the jargon of philosophy. In this video we're going to be taking a look at what is the Thompson's lamp paradox. Now, the Thompson's lamp paradox, proposed by J.F. Thompson, is a paradox for a lamp that starts off and then turns on or off, switching statuses, first after 1 minute, then after 30 seconds, then after 15 seconds, then after 7.5 seconds, etc. So it turns on after 1 minute, off after 30 seconds, on after 15 seconds, etc. The question is, what state is the lamp in at exactly 2 minutes? Now, the Thompson's lamp paradox is a variant on one of Zeno's paradoxes. Achilles and the tortoise are in a race. Achilles, being a good sportsman, gives the tortoise a 1 mile head start. By the time Achilles travels 1 mile, the tortoise has traveled a little bit further. The tortoise has traveled half a mile. Again, by the time Achilles travels that half mile, the tortoise has again moved a little bit further. They've moved now a quarter of a mile. The problem is that Achilles will need to travel an infinite number of distances to catch up to the tortoise, because by the time Achilles catches up to where the tortoise was when he started running the last time, the tortoise will have always moved a little bit further. Zeno was concerned that Achilles couldn't move an infinite number of times, and so movement was in some way impossible. However, this paradox was solved by the advent of calculus. We are able to find the sums of infinite series by calculating the limit that they converge towards. The sum for Achilles and the tortoise converges to 2. 1 plus 1/2 plus a quarter plus an eighth plus a 16th, etc., 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 converges to 2. So Achilles will catch the tortoise at the 2 mile mark. A similar solution can be applied to some of Zeno's other paradoxes. We can solve puzzles involving an infinite number of steps by looking at the limit that those puzzles converge towards. This is what makes Thompson's lamp a more problematic paradox than Zeno's original paradox. The infinite series of 0, 1, 0, 1, 0, 1, 0, 1, 0, and so on might be used to represent the state of the lamp, where 0 represents off and 1 represents on. However, this series does not converge to any real number in the traditional sense. Therefore, the same argument that solves Zeno's paradox cannot be used to solve Thompson's lamp. One attempt at resolving this paradox is to look at the Cesaro convergence, effectively the average of a sequence. The convergence of the sequence in this case is 1/2, the average of 0 and 1. The problem with this as a solution is it's not clear if 1 represents on and 0 represents off, what 1/2 would represent. It seems that in this model we don't have any explanation for what half of being on or off, or some superposition between on and off, would really represent. And so there's a concern that this mathematical explanation couldn't map onto, in some way, the reality of the situation. So there's still this concern of what exactly is the lamp doing at 2 minutes? Is it in some weird superposition between on and off? That seems strange. Now, one claim is that this paradox is underdetermined with the information provided. In other words, there are multiple possible situations that this paradox could describe, each with different outcomes. The reason we can't tell if the lamp is on or off is that you haven't provided us with enough information, and that with more information we could duplicate the same or a very similar situation and determine whether the lamp's going to be on or off. For example, imagine that there is a ball bouncing on a metal plate. The ball's connected to the lamp, and whenever the ball makes contact with the metal plate, and so is the plate, it completes the circuit and switches the lamp on. The ball bounces such that it is first in the air for 1 minute, then for 30 seconds, then for 15 seconds, etc. This ball doesn't follow the normal laws of physics, and so it is going to bounce an infinite number of times, getting smaller and smaller in each amount of time every time. Similar to the original Thompson's paradox, the lamp is going to switch status an infinite number of times, because that ball is going to bounce an infinite number of times, getting faster and faster and faster as it goes down. But it's also clear that when the ball comes to rest on the plate at the end of 2 minutes, it completes the circuit, and the lamp is going to be on at 2 minutes. Conversely, we could imagine the same scenario, but when the ball makes contact, it breaks a circuit. So the plate is connecting a circuit, and the ball depresses the plate slightly and breaks that circuit, meaning that the lamp will switch status an infinite number of times, but when the ball comes to rest, it will be off. Now, these may make the case for this being an underdetermined paradox. The reason we can't decide is because we don't have enough information, and both of these scenarios seem to replicate the situation going on. But there's also part of me that wonders if we are being biased by the situation, i.e., what we're actually assessing is whether the lamp is on or off half a second or an instant after 2 minutes, because we know that an instant after 2 minutes the ball is going to be resting on the plate, and therefore either breaking the circuit or not breaking the circuit. What we're not actually sure of is whether the ball is making contact at 2 minutes exactly. And so it may not be a problem of underdetermination, but rather these particular thought experiments may be pushing us in one direction or another. Problems like this in philosophy are sometimes called supertasks, where there is an infinite number of steps required to accomplish the task. Stay tuned for more videos on other paradoxes. There's a lot of paradoxes related to supertasks, so stay tuned for more videos on these, as well as for a video on supertasks in general coming up. But for now, what do you think? Is Thompson's lamp on or off at exactly 2 minutes? Is it in some superposition between on and off? Is our example insufficiently described for you to be able to tell? Or is this not an important question, since unlike Zeno's paradox, it's not physically possible to actually turn a lamp on and off an infinite number of times, and so this is something for mathematicians that doesn't have any real bearing on reality. Leave your thoughts in the comments below, watch this video and more here at Carneades.org, and stay skeptical, everybody.